Have you ever wondered that where does the water that we get through the wells come from? To know this, let us first see how rocks occur underground. Below the ground, the rock units generally occur as layers stacked one above the other. Some of these rocks have openings within them called pores, and these pores may be filled with water. Such rock units which have pores filled with water and are capable of yielding water are known as aquifers. In this simplified diagram, the blue-colored layers represent aquifers. Wells are so constructed that they draw water from these aquifers. It is possible that water in some of the aquifers is fresh and in some others it is saline. Again, it is not necessary that the aquifers will always be horizontal. They may be inclined, also something like this. In this backdrop, the National Aquifer Mapping and Management Program, also known as the NAQMIM, is taken up with 6 major objectives: delineating the horizontal and vertical extents of the aquifers, evaluating properties that control occurrence and movement of water in the aquifers, assessing chemical quality of water and its suitability for use, estimating different recharge and discharge components, identifying and quantifying the issues, preparing aquifer management plans. The management plans thus prepared are shared with the state governments and the stakeholders at the grassroots level. A combination of various scientific tools and techniques are used for delineating and characterizing the aquifers. Hydrogeological mapping tells us about the extent of the aquifers. Geophysical investigations provide indirect information about disposition of the aquifers beneath the surface. Drilling-assisted groundwater exploration provide a lot of direct information regarding depth-wise extent of the aquifers and properties. Pumping tests are carried out to know the storing and transmitting capacity of the aquifers. Chemical quality is assessed in the laboratories. Water levels are measured through the piezometers. All this information are synthesized to prepare 3D aquifer models, characterize the aquifers, estimate quality of water, and assess volume of water entering into and going out of the aquifers. Based on this information, the management plans are prepared. 2 basic aspects of management strategies are supply management, that is, augmenting the groundwater resources. This can be done through artificial recharge or managed aquifer recharge by construction of percolation tanks, recharge shafts, check dams, or similar structures. The other strategy is demand management or reducing the consumption. This can be achieved by improving irrigation efficiency through use of micro-irrigation techniques like sprinklers or by adopting less water-consuming crops, etc. The management strategies recommended as a part of NAQMIM involve both supply as well as demand-side measures based on aquifer properties and other conditions. The final step is taking the outputs, the maps, and management plans to the public. The outputs are shared through reports and other forms through the website of CGWB. The maps and management plans so prepared are shared with state governments through the state groundwater coordination committees. To reach out to the groundwater users at ground level, CGWB carries out block-level training programs and public interaction programs. The studies completed so far have provided several newer insights into groundwater scenarios and management alternatives. NAQMIM program is helping in plugging the knowledge gaps and empowering the stakeholders with usable information for sustainable management of groundwater resources in the country. Coimbatore district, nearly 500 km west of Chennai, is blessed with scenic beauty, like hill stations. Ukkadam Lake. It is also known for its many temples and the famous Adiyogi statue. Economically, it is one of the most advanced districts in the country. And a sizable part of the economy is attributed to agriculture. Maize, cholam, coconut, banana, rice and sugarcane are some of the major crops taken in the district. Normal rainfall in the district is around 500 mm. The district is heavily dependent on groundwater. As per the District Statistical Handbook of the Government of Tamil Nadu, 85% of the total irrigation requirements are met from groundwater. The aquifers, that are the sources of groundwater, are under severe stress. The aquifer systems in the district are part of the Amravati Aquifer system, which is the most important source of fresh water for drinking and irrigation in the western part of Tamil Nadu. CGWB took up detailed aquifer mapping in this area as a part of the National Aquifer Mapping and Management Program with the objective Know the Aquifer and Manage the Aquifer. Major part of the district is covered with granitic rocks that are hard rocks with limited groundwater potential. Aquifer mapping studies brought out presence of two aquifer systems. The first aquifer extends from ground level to a depth ranging from 7 to 45 meters. Weathered granitic rocks form the first aquifer. Below this, the second aquifer is identified down to the depth range of 11 to 200 meters. Up to 4 water-bearing fracture zones are encountered in this range. There are also locations which are devoid of the fractured aquifer system, and groundwater occurs only in the topmost weathered layer. With nearly 70,000 abstract structures that include open duct wells and bore wells, a huge amount of water is pumped from these aquifers. Every year, nearly 365 million cubic meter of water is recharged through rainfall and other sources. And as high as 450 million cubic meters of water is extracted from the aquifer, which is much more than the annual recharge, making it overexploited. As a part of the NAQUIM studies, based on aquifer configurations, their properties and other factors, a management plan was prepared which included recommendations for various demand-side interventions like use of water-efficient irrigation techniques, cultivation of less water-consuming crops, and supply-side management interventions like construction of artificial recharge structures. As a part of the supply-side interventions, the NAQUIM studies recommended construction of 155 bunds, renovation of 220 ponds, and construction of 716 recharge shafts in 16 most water-stressed firkas of the districts. Detailed locations and designs of the recommended sites were handed over to the District Rural Development Agency, DRDA, Coimbatore. The District Rural Development Agency, Coimbatore, under the Jal Shakti Abhiyan program, implemented the recommendations of the NAQUIM studies for construction of the artificial recharge structures. Structures like Gabion dams with recharge shafts, and check dams were constructed. Old village ponds were restored like this one in Thettipalyam village of Madampatti Firka. Defunct borewells which used to yield water were converted to recharge structures. The interventions have clearly shown increase in water levels and improvement in sustainability of wells. Better understanding of aquifers is helping in planning and implementation of cost-effective and efficient recharge interventions. Groundwater contamination has emerged as a major challenge in ensuring safe drinking water supply from aquifers. To overcome pathogenic contamination in surface water sources or dug wells, hand pumps and bore wells were promoted in a massive way as safer sources for drinking water. However, surfacing of geogenic contaminants like iron, salinity, nitrate, arsenic, fluoride, etc. has offered a fresh challenge. In this video, we will discuss about the instances of high arsenic in groundwater in India and the initiatives of CGWB in remediation of arsenic contamination. Arsenic occurs naturally in groundwater, but only as a trace constituent. When its concentration in drinking water exceeds a certain limit, it is known to have many adverse health effects. As per the Bureau of Indian Standards and also as per the standards of World Health Organization, the safe limit of arsenic is 10 parts per billion. That means 100 liters of water should have less than 1 milligram of arsenic to be fit for drinking. Prolonged exposure to arsenic-contaminated drinking water may result in gastrointestinal diseases, cardiovascular disorder, and even cancer. However, the most common effect is hyperpigmentation of skin and keratosis. As per the studies carried out by the CGWB, arsenic is found in parts of 152 districts in parts of 21 states, and approximately 40 million people are residing within the risk zone of arsenic contamination. However, it is important to note that in an affected districts, not all blocks are affected. In an affected block, not all villages are affected. In an affected village, not all the borewells or sources are affected. The largest contiguous belt of high arsenic in groundwater in India is the Ganga Plains. In this part, arsenic contamination has been reported from nearly 66 districts in 6 states: West Bengal, Uttar Pradesh, Bihar, Jharkhand, Haryana, and Delhi. The recent aquifer mapping studies have helped in delineating multiple aquifers in these areas, and in general, the deeper aquifers are arsenic safe. This is a schematic diagram showing that the upper aquifers with high concentration of arsenic is separated from the arsenic safe deeper aquifer by a thick clay layer, such that water in these two aquifers do not get mixed. This means that if we can construct a well that gets water from the deeper aquifer and do not allow arsenic contaminated aquifer in the shallow aquifers enter the well, we can ensure contaminant-free drinking water through this well. CGWB introduced the technique of use of cement sealing within the wells so that it can provide arsenic-safe water. In this technique, first, the pilot hole is drilled. After drilling of the pilot hole, a pipe called the well assembly of nearly 6-inch diameter is lowered in the well. This well assembly is perforated only at a particular place so that the perforations are placed against the aquifer, releasing arsenic-safe water. The annular space between the well assembly and the wall of the well is filled with gravel, and at appropriate depth, cement slurry is put, which solidifies and prevents arsenic-contaminated water to reach the screen through which water enters the well. Thus, the water that is extracted from the well is drawn from the deeper aquifer and is arsenic safe. It is important to note that such cement sealing is not sufficient. Controlling the pumping rate is also important to keep the water level in arsenic protected aquifers higher than in contaminated aquifer, so that the water from the contaminated aquifer does not flow like the deep aquifer or the arsenic protected aquifer. Using this design, CGWB has constructed nearly 600 wells in parts of Bihar, Uttar Pradesh, and West Bengal. State governments of Uttar Pradesh and West Bengal have constructed nearly 1500 such wells with cement sealing that are catering to the safe drinking water requirements of nearly 70 lakh people. Aquifer mapping is helping in better understanding of aquifers and offering innovative solutions to many problems.